Hello everyone, my name is Kathan and today we'll be discussing the problem 2 nights from the Introductory Problems of the CSES Problem Set. Let's begin. Let me read out the question for you. A task is to count for k equals to 1 to so on till n. The number of ways 2 knights can be placed on a k by k chessboard so that they do not attack each other. So input will simply contain integer n, which turns out here goes from 1 to 10 power 4, right? So this is 10,000, and we have to go from k equals to 1 till n. So here if n is 8, you have to go from k equals to 1, 2, 3, 4, 5, 6, 7, 8. And for each value of k, you have to consider a k by k chessboard. You have to output number of ways to place 2 knights or horses in chess in such a way that they do not attack each other. Right? So the question is as simple as it can get. For input n, you find for chessboards 1 by 1, 2 by 2, 3 by 3, so on till n by n, number of ways to place 2 knights such that they do not attack each other. So that's the question. So here are some test cases, and for example, like if you have a chessboard of 1 cross 1, of course, like you will have to place both the knights on the same cell. So in that case, of course, there is no way to place 2 knights such that they do not attack each other. Like if you place both of them in the same cell, it's not possible, right? So that's why it's 0. And let's go to the iPad and discuss this test cases further so we can get a more idea of this question. First things first, let's see how a knight moves in chess. So a knight moves in L shape, in the sense it moves 2 steps in one direction followed by 1 step in other direction, 2 steps vertically followed by 1 step horizontally, 2 steps in one direction followed by 1 step in other direction, 2 steps horizontally followed by 1 step vertically. Right, so all in all it can attack 1, 2, 3, 4, 5, 6, 7, 8. So it can attack 8 places at max. Why at max? Because like if you have a knight here in this border locations from which you cannot go 2 steps in one direction, then some places will be reduced, right? So 2 things are important here. A knight moves in L shape and it can attack 8 positions at max. Fine. Let's see a test case here and try to make sense of the question. So we have, let's say, n equals to 8. So what do we have to do now is we have to consider chessboards of size 1 by 1, 2 by 2, 3 by 3, so on till 8 by 8, and for each chessboard we have to find number of ways we can place 2 knights such that they don't attack each other. Let's take an example here. Let's say we have a chessboard of size 1 by 1. So 1 by 1 means simply one chess, like one cell, right? So here of course, like if you have only one cell, there is no way to place 2 knights in a way they don't attack each other, because both of them will be placed here itself. So of course here answer will be 0, right? So you have to print here 8 outputs. So the first output will be 0. Fine. Let's consider a case where we have 2 by 2 chessboard. 2 by 2 chessboard looks like this. 2 by 2, or you can say there will be all in all 4 cells here. Fine. Now how can you place 2 knights here in such a way that they don't attack each other? Now see one thing here, like you place a knight any which way, you won't be able to perform any move from this knight, right? Because it has to move 2 steps in one direction. But in a 2 by 2 chessboard, there is not enough room such that a knight can move 2 steps in one direction. So what it says is you put those 2 knights in any way and they will not attack each other. In the sense, your answer is simply total ways to place 2 knights on this chessboard, like 2 by 2 chessboard, or you can say on 4 cells, right? Or if I want to simplify it, you have n positions to choose from, like you have total all in all n positions, and you have to select 2 positions to place this knight. So it's a classical permutation combination question. You have n places and you have to choose 2 positions in it where you have to place the knight, because in any 2 positions you put, it will be a valid placement, right? The knights won't attack each other. So here the answer comes out to be nc2, which is 4c2. So 4c2 is what? It's 4 into 3 divided by 2 into 1, which turns out to be 6. Right? So if you are confused about this formula, why this formula makes sense, I'll show you. Now this is a classical permutation combination question here. The total ways to place 2 knights on a, you can say 2 by 2 chessboard will be simply 4c2, where 4 being the total number of cells. So let's see, like if you don't know this formula, how can you derive it? So that will be also a good interesting exercise here. Now you want to find out how many ways are there to place 2 knights on this 2 by 2 chessboard. So what you can do is like you can place, let's say, first knight here, and then you have three options to choose from to place the second knight. So these are, you can say, three ways, right? When you place the first knight on the first cell, fine. Then let's say you decide to put the first knight here in the second cell. You have three more ways to choose where you can place the second knight. So these are three more ways to place the knight, right? Place two knights. Similarly, you may decide, let me put the first knight on the third cell here. So there are three more ways to place the second knight. So this gives you three more placements, right? Similarly, you may decide that I'm gonna place the first knight on the fourth cell. So you have three more ways to place the second knight. So this also gives you three more. So this is what? This is actually 3 into 4. But this turns out to be 12. But our answer is 6. Why? Notice one thing here. You are overcounting. In the sense, one placement is counted twice. I'll show you. Let's say we have this placement of knight. Now this placement is counted twice. This placement is counted once when you place the first knight here and second knight here, and first knight here and second knight here, right? Similarly, I'll show you every placement is counted twice here, like in this 3 into 4. If you place first knight here and second knight here, this placement is over counted. Why? This is as same as first knight here, second knight here, and first knight here, second knight here. That's why you have to divide it by 2. So this also turns out to be 6, right? So we have seen two ways. One is the standard NC 2 ways, and the other one is using the, you can say, fundamental laws of counting, addition, multiplication. Fine. So any which way, what I'm saying is the total number of ways to place two knights on a chessboard of size here k by k will be, let me just denote total cells to be TC, not test case. These are total cells. So total number of ways to place two knights on a chessboard will be TC into TC minus 1 by 2, which is nothing but NC, like TCC2. Fine. So these are total number of ways. Okay, fine. So what about 3 by 3? So here answer is 6, right? So for 2 by 2, the answer is 6. Here the answer was 0. Okay, fine. Now what about 3 by 3? In 3 by 3, the chessboard will be of size this 3 by 3, so there will be 9 cells. Now here you can definitely have attacking positions, right? So you can have a knight, let's say here. If you put the first knight here, you don't have 8 as the remaining. You cannot put knight on all the possible 8 positions left. Why? Because if you put a knight here, they will attack. Right? If you put a knight, it will attack. So here it is not as simple as this total number of ways to place the two knights, because here a knight can move 2 steps in one direction and it will cause two knights to attack each other. For example, if you place a knight here, you cannot place a knight here, right? Is there any other place? No, right? So it cannot move 2 steps horizontally, but 2 steps vertically it can move in this direction, right? So here, like, you will have to subtract some placements. So similarly, like for all the cases afterwards, there will be placements where which you can place two knights in a way that they will attack each other. So to approach the question, what you will have to do is from the total ways, you will have to subtract, you can say, number of attacking placements, right? So this will actually give you total number of ways to place two knights in such a way they don't attack each other. Because you know what are the total number of ways to place two knights on the chessboard. From that, if you just subtract number of attacking placements, that is number of ways to place two knights such that they attack each other, this will actually yield our answer, right? Yield our answer, which is total ways to place two knights. Knights spelled like this, two knights on a k by k chessboard, or you can say on TC number of cells such that they don't attack each other, right? So that's how we can figure out the approach here. So you have total ways, just subtract from it the number of attacking placements. Now how do you figure out the attacking placement? That's an interesting question. Now let's just try to see from the chessboard itself. Let's try to dry run through some of the cases here and see if there's some pattern, because in this sort of questions there will surely be a pattern where you can observe to find, like, what we are after. We want to find that what are the number of attacking placements, right? So this is what we want to find. Let's just see. Okay, now what I'll do is I know that a knight can move in L shape, right? So L shape means it either moves 2 steps horizontally followed by 1 step vertically, or it moves 2 steps vertically followed by 1 step horizontally. So let's just take it step by step. Let's first consider a case where a knight only moves 2 steps horizontally, right? So let's just see if we can figure out a placement that way, and then we'll figure out what happens if a knight moves 2 steps vertically and try to make some observations here. Fine. So let's say our first knight is here. Now if this knight moves 2 steps horizontally, what will happen is it will attack in this direction, right? So it is gonna attack this guy here. So let me just denote by triangle here. So these two are gonna attack each other. Fine. Let's say if you have a knight here, so this is gonna go 2 steps horizontally and then gonna attack like this. So this is gonna attack this one. So these two are gonna attacking each other, right? So in a way, this is one attacking placement. This is one attacking placement. Fine. Let's say I have one more. Let me denote it by X. So this can move 2 steps in this direction. It can also move 2 steps behind as well, right? So there are 2 places here where it will be attacking. So this position and this position, right? So this forms an attacking placement. This forms an attacking placement. Fine. What else? Let's take one more example here. Let me draw a square here. I'm running out of shapes, but this guy, this cannot move in this direction horizontally, so we'll try to move back, so horizontally, and it's gonna attack this guy. Fine. Let's take one last one, then why leave it? Let's just call it as a diamond shape. Okay, this guy is gonna attack here only. Fine. What do you see here? Can you see some pattern here? I don't know if you can see it. So notice this thing. This portion. So this portion, do you see something here in this portion? In this portion we have this attacking placement and this attacking placement, right? Similarly, in this part there is this attacking placement and this attacking placement. Similarly, in this portion there is this attacking placement and this attacking placement, right? There is nothing here, so fine. So all in all, what I'm trying to show you is, you see this block. You see this block. There are 2 attacking placements. One is this one is this one, and one is this one. Similarly, you see this block. You see this block. There are 2 more attacking placements here. This one and this one, right? Let's see one more then. In this block as well, you can see this one attacking placement and one attacking placement, right? So what do you see here? Like, what is this block? This block is of size 2 by 3, right? 2 rows and 3 columns, right? So a block of size, or you can say a slab of size 2 by 3 has 2 attacking placements, right? Has 2 attacking placements, and these 2 are unique as well. Like, for example, you consider any 2 by 3 slab. If you have a 2 by 3 slab here, you will have attacking placement here. So this one and this one, right? You have a 2 by 3 slab here, you have an attacking placement here, and an attacking placement, for example, this attacking placement is unique as well to this slab. You will not find this attacking placement in any of the 2 by 3 slabs below, right? Because like these 2 are not part of any of the 2 by 3 slabs, right? So you have any 2 by 3 slabs here, any 2 by 3 slabs, you'll always find 2 unique attacking placements, right? So this observation is very crucial here. This is a very crucial observation. Every 2 by 3 slab contributes 2 attacking placements, right? So what we are doing is effectively we are trying to see what happens when a knight moves 2 steps horizontally. So when a knight moves 2 steps horizontally, what we happen to find out is every 2 by 3 slab, why it is a 2 by 3 slab? Because we are trying to figure out if a knight moves horizontally. That is the reason this slab spans in this direction, in you can say y direction. That's why you got a 2 by 3 slab. It contributes to attacking placement. So this is interesting, right? So from the total ways, from total, now you can subtract number of 2 by 3 slabs, right? You can subtract number of 2 by 3 slabs in a k by k matrix or grid, right? K by k grid. Right? So how to find this number of 2 by 3 slabs is another question, but now we can subtract this, right? So now we are closer to our answer. But what next? Like here we have only considered the case where a knight can move horizontally, but a knight can move vertically as well, right? So let's just take that case as well. Let's say we are considering knights here. So I can actually consider this knights as well, but it will otherwise clutter the examples here. But let's just take the knights of the last row. So we have a knight here. If it decides to go vertically this time, it can attack this knight, right? Let's say we have a knight here. If it decides to go vertically, it can attack somewhere here and here. So it can attack in these two positions. Similarly, let's say we have a knight here. So it can attack in these two directions. So it can attack here, here. Similarly, let's say we have a knight here. It can decide to attack here and attack here. One last, the diamond one. This knight can attack here as well. Only here, right? So it cannot attack here because it will go out of bounds. Fine. Do you see one more pattern here? I think you will be able to see. Notice this slab. You have one attacking placement here, one attacking placement here. Notice this slab. You have one attacking placement here, you have one attacking placement here, right? Notice this slab. You have one attacking placement here, one attacking placement here. Similarly, this slab, you have one attacking, okay. You have one attacking placement here, here. And every attacking placement, for example, here, this attacking placement is unique to this, what, 3 by 2 slab. Also, this is not going to occur in any of these 2 by 3 slabs, right? This 3 by 2 slabs, every 3 by 2 slab contribute to attacking placements, right? They contribute to attacking placements. And these are unique as well, right? If you have an attacking placement here, this will not be part of any of the other 2 by 3 slabs. Also, they will not be part of any of the attacking placements in this 2 by 3 slabs. For simple reason that here, the two attacking knights, you are taking 2 vertical steps. But in every attacking pair of knights here, you are taking 2 horizontal steps. So any which way, there will never be an overlap between these placements and these placements. So these are, you can say, mutually exclusive attacking placements, right? So what we have figured out is from the total, first you subtract number of 2 by 3 slabs. So this is the case. So this is the case when we move 2 steps horizontally followed by 1 step vertically, right? And from that you also subtract now number of 3 by 2 slabs. So this is gonna contribute when a knight moves 2 steps vertically and 1 step horizontally. So if you effectively covered the cases where a knight moves 2 steps horizontally followed by 1 step vertically and 2 steps vertically followed by 1 step horizontally, you have covered all the possible ways a knight can move. So this is your answer, right? So this, you can say, you are definitely consider all the cases where knight can move, and from the total number of ways to place 2 knights, you just subtract the number of attacking placements. So the key argument here is every placement here, every placement here, every placement here, every placement here is unique to its slab. It will not be part of any other slab, right? So yeah, I mean, that's about that. All that remains is how are you gonna find the number of 2 by 3 or 3 by 2 slabs. How to find a number of 2 by 3 and 3 by 2 slabs? What I'm gonna do is I'm gonna first find out how many of those, like let's say for example, how many of 2 by 3 slabs I can put it in a single row, then I'm gonna multiply it with how many 2 by 3 slabs I can put in one column. So this will effectively give me the number of total 2 by 3 slabs, right? So let's just see the case for 2 by 3 slabs, and then we can do the same for 3 by 2 slab, although it will be symmetric if you can see it, but fine. So first 2 by 3 slab, I'm just calculating number of 2 by 3 slabs I can put in one row. So this is gonna start from here, right? Then another 2 by 3 slab is here, so it's gonna start from this part, this edge. Then another one will be here, so it's gonna start from this edge. Similarly, one of these will start from this edge, so 4, and then one of those will start from this edge. Now you cannot start from you cannot start from either this edge or this edge because like you don't have enough cells in horizontal direction. Fine. So you have you can put 5 2x3 slabs in one row. Now let's see the case for how many of those you can put in vertically, like one column. So one 2x3 slab is this only, right? So one 2x3 slab is this only. The another one can be like this, right? The another one can be like this here. Similarly, one of them can start from here. So this part. Similarly, one of them can start from here, this part, and one of them can start from here. 6, right? So all in all, you cannot start from this edge here because you don't have enough cells to span vertically. So what is our answer here in case of, let's say, 7 by 7 grid? So in case of 7 by 7 grid, your answer is here 5 into 6, or effectively when you're trying to place it in a row, you cannot use 2 edges, and when you're trying to put it vertically, you cannot use 1 edges. So the generalized answer would be here m minus 2, right? So these many you can put in one row into m minus 1, this many you can put in one column. So the total answer will be m minus 2 and m minus 1. Now what about 3 by 2 slabs? This will be symmetric, right? So you can just flip the matrix and see it. It will be same, but just for completion's sake, I'll show you. So the answer will be same here also for 3 by 2. So here, let's just see the case for 3 by 2 slabs as well very quickly. For example, one 3 by 2 slab can be here. So I'm trying to put 3 by 2 slabs this time horizontally. So one of them will start from here. One of them will start from here. Similarly, this will start from here, 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 but it cannot start from here because like it cannot use this edge to start because it won't have enough cells to span. So 6 again, right? So it will be 6 in one row. And how many columns? I guess you would have guessed it. It will be 5 only, but let's just do it anyway. 1, 2, 3, 4, 5, right? You cannot start from either this edge or this edge. So again, the answer turned out to be 6 into 5. 6 into 5, right? So again, it will be m minus 1 into m minus 2. So this portion, what will it be? First, find out the number of 2 by 3 and 3 by 2 slabs. It will be 2 into m minus 1 into m minus 2. So this will be total number of 2 by 3 and 3 by 2 slabs. And from each one of these slabs, you get 2 attacking placements. So into 2. And this part, like this part, you can subtract from the total. So total is what? It will be k square c2, right? Total number of ways to place 2 knights. And that will be your answer. So I hope you have understood the explanation till now. From the total ways to place 2 knights, we are just subtracting the attacking placements. And if you have understood it, please comment understood in the comment section of the video right now. And then we can move on to the code and the time complexity and space complexity discussion. Alright, so here's the code. First we take the integer input n. Why integer? Because n can go as high as 10 power 4, so we can store it in an integer. And then we go from k equals to 1 till n, that is consider the chessboards of size 1 cross 1, 2 cross 2, so on till n cross n. Then find total number of cells. So here I am taking total number of cells as long. Why long? Because it will be later involved in multiplication and all, so it can cause overflow. That's why I'm converting to long only. If k equals to 1, that is if the chessboard size is 1 cross 1, there are no ways to place 2 knights because you have just a single cell, so output 0. Otherwise, calculate the total ways to place 2 knights and then calculate the contribution from the 2 by 3 and 3 by 2 slabs. So this are total number of 2 by 3 and 3 by 2 slabs, and from each slab you have contribution of 2 attacking placements, and then subtract it from total, and that will be your answer. And the time complexity here, you can say you are running a loop of n, and here this all is a constant time operation, so it will be order of n or order of 1e4. And space, you are not using extra space, so order of 1. So I mean, yeah, that's that. If you want, I can run it as well. I can run it. So this actually gave you the same results here if I ran it, right? So that's about this, I guess. I hope you liked the video. If you did, please give a thumbs up, and I'll see you in the next one.